So with the tangent and the cotangent, there will be amplitude changes. Well, actually, tangent and cotangent don't really have amplitudes, but there's going to be period changes. With these two, there aren't going to be horizontal or vertical shifts going on. Okay? With cosecant and secant, there are going to be. Okay? These ones are difficult enough as it is without having to worry about phase shifts and vertical shifts and things like that. It's not something you're going to have to know in calculus at least. So let's talk about tangent first of all. Matter of fact, get your unit circles out if you have it handy. What was normal? I'm talking normally here. What was the normal period of sine and cosine? Normally, with no phase shifts or amplitude or anything, any kind of changes. 2 pi. Why is that? That goes around a full circle, right? After you go around a full circle, don't you just start repeating yourself with sine and cosine? Would you also start repeating yourself with tangent if you go around a full circle? Just something to think about here real quick. Don't even really need to take notes about this or on this. What's the tangent of 30? What's the tangent of 30 degrees? It's 1/2 divided by square root of 3 over 2, right? Which, if you simplified, would be 1 over the square root of 3, which is square root of 3 over 3. What about the tangent of a full 30 degrees and then a full revolution? What would that be? 30 degrees and then a full revolution. But what's the angle measure? So what's the tangent of 390? Wouldn't it be the same thing? My question to you is, though, square root of 3 over 2. Square root of 3 over 3. Do we have to go a full revolution to get that same exact answer? Or is there a shorter distance we can go around the unit circle to start repeating itself? Think carefully about how we defined tangent. Isn't it y over x? The definition of tangent is y over x. Go ahead.
So if you added 180 degrees,
Why? You are absolutely right.
it's negative y over negative x.
If we added 180 degrees to this angle right here, for example, wouldn't we end up in the third quadrant? But in the third quadrant, aren't y and x both negative? A negative divided by a negative is a positive. So the point here is you don't have to go a full revolution to start repeating yourself with tangent. How far do you need to go? Half a revolution, which is pi. So the period instead of 2 pi divided by b, the period is going to be pi divided by the absolute value of b. That's one difference. One difference is the way that you find the period. It's pi divided by b. Another difference, and this is a pretty big difference. There are vertical asymptotes. There are vertical asymptotes because there are domain restrictions. This goes back to this right here. The tangent of an angle is equal to y over x. That means wherever x is equal to 0 on the unit circle, guess what? There's a vertical asymptote there. So take a look at your unit circle. Start naming off some angles for me where you have x values of 0. Vertical asymptotes. Pi halves. Where else? 3 pi halves. Where else? Where's that coming from? You're just going around the unit circle. Where else would you have vertical asymptotes? Okay, go the other direction. We're only going one way around the unit circle. Negative pi halves. Where else? You get the picture, right? Why these angles in particular? Why these angles?
This is where x equals 0 in the unit circle. If x equals 0, we would be dividing by 0.
So you're going to have vertical asymptotes here. Normally, if the period remains unchanged, if the period is pi, this is where your vertical asymptotes are going to be. If the period changes, that affects the location of vertical asymptotes. So just for the sake of ease, let's graph a normal tangent function with no changes whatsoever. Y equals the tangent of x. What's the period? It's pi divided by the absolute value of b, where b is the coefficient of your variable. So it's pi divided by 1, which is pi. So that means the horizontal distance to complete one cycle is pi units. Where are the vertical asymptotes going to be? There's a lot of them. How many are there actually? How many vertical asymptotes are there? Infinitely many. Just keep going around the circle. So where would some be? Pi halves. So put a vertical asymptote at pi halves. Negative pi halves. Put a vertical asymptote at 3 pi halves. Negative 3 pi halves. And so on and so on. Since we're not entirely sure of the shape of this graph, let's start plotting a few points, starting with x equals 0. Now remember, we're talking about radian measures here. X represents radian measures, so look at your unit circle with a radian measure of 0. What's the point on the unit circle with a radian measure of 0? Let me draw a quick little circle right here. This point right here, at the right side of the unit circle, that's the location of 1, 0, right? So what would the tangent of that be? 0 over 1, which is 0. So there's a point on the tangent function, 0, 0. Would this be a very wise choice for x, pi halves? Why not? There's a vertical asymptote there. There aren't any points of a graph on a vertical asymptote. A graph never crosses through a vertical asymptote. This is kind of a difficult question. You need to think back to what chapter? It was a while ago. We've seen a couple of graphs that have vertical asymptotes. What's the behavior of a graph as it nears a vertical asymptote? Does it just stop? It gets closer and closer and it goes up to infinity, or it gets closer and closer and goes down to infinity. Keeping that in mind, I mentioned this briefly, but you might not have heard it. These graphs don't have an amplitude. Tangent doesn't have an amplitude. Why is that? The graph goes up to infinity and down to infinity without end. An amplitude is a measure of a vertical distance. Is there a measure of a vertical distance if it goes up and down forever? No, that's why there's no amplitude here, just a period. So what we have to decide is we know the graph is eventually going to pass through 0 and head towards its asymptote. Does it go up or does it go down? So let's choose a point between 0 and pi halves. What would be a good choice? Pi fourths. All right. What's the tangent of pi fourths? Look at your unit circle. It's 1. Yeah.
So unlike the cosecant and the secant, there won't be an amplitude, right?
Correct, because they go up and down forever and ever, yeah. So at pi fourths, we're up at 1. What about negative pi fourths? Negative 1, so at negative pi fourths, we're down to negative 1. Guess what we just graphed right there? One cycle of the tangent function.
Don't they all look like that now?
That's what I was just going to ask you. Reading my mind, Megan. What would the graph look like in this region right here between pi halves and 3 pi halves? Exactly the same as that. What about in this region over here between negative pi halves and negative 3 pi halves? Exact same thing. So if I only require one cycle of sine and cosine, all I require is one cycle of tangent. So this would be sufficient right here, just this one cycle. Does that make sense? But just because we're learning, let's be a little
more detailed. Where would the graph pass through when we're at pi? 0. And then halfway through each of those, we'd be up at 1 or down at negative 1, just like in the other cycle, right? So it would look like that. Over here at negative pi, we're at 0. Halfway we're at 1. Halfway over here, we're at negative 1. Now we've got 3 cycles of the tangent function.
What's the formal definition of period?
The distance it takes to complete a cycle.
The distance it takes to complete a cycle. Let's just double check. One of our cycles here, this one for example, this cycle started at negative pi halves and the cycle ended at pi halves. What's that distance? It's the distance of pi, right? From negative pi halves to pi halves.
But it's not like a distance that doesn't equal to
Well, infinitely close, there really is no discernible distance from being there or not being there. That's the whole idea of a limit, which you'll talk about next year in calculus. But yeah, that's a good point.
Well, for that, would you like us to read it like greater than and less than, and like put it in the distance?
For
Or like when we like distance, or like greater than.
it's still correct to say the period is pi. What about this one? Let's do part B. What starts to happen when we change the, I don't know, let's change the period. Y equals a tangent of 2x. Yeah.
How would you write the domain of a trig?
Whoa. How would you write the domain?
I feel like you just need to.
Why would you do that? You don't need to.
If you're asked, I'm not going to probably ask it on a test, but that's a good question. How would you? Is this correct?
No.
No. Man,
Maybe you can use sequences.
it's not a bad thought.
You could like say like every this number.
Do you remember set builder notation? Did we talk about
Yeah,
set
I
builder
remember
notation?
this.
So, x does not equal. What does x not equal? Here's the problem. Would it be very smart to list an infinite number of numbers that x can't equal?
Do pi halves x.
Ooh, keep going. X does not equal pi halves.
Where x is an integer.
Okay. We already have x here representing our input, so let's not use x.
Or s.
Let's use n. It's actually more typical in most textbooks to use n. X does not equal pi halves n, where n equals
A whole number.
what can n? What if n equals 1? What do we get here? Pi halves. What if n equals 2?
N equals
So we don't want n to be integers. Odd? Okay, that would be an acceptable way. N equals odd integers. Now, there is a little more sophisticated way of writing that. What would be a good way of always getting odd numbers? There you go. Where n is an integer. What's an integer? Positive, negative numbers. An integer such that it equals 2n. 2n plus 1. I mean, this is getting more into a calculus type discussion. I'm certainly not gonna expect you to do this here, but if it's 2n plus 1, that's gonna generate odd integers. And that's what we want, is odd multiples of pi halves. That's a good discussion for a later time. Back to this one, y equals tangent of 2x. What's happened to the period? Well, here's a question. Has the period increased or decreased? What do you think? Remember the phrase inside the function. Isn't that inside the function? Inside the function is opposite. So common sense would say, well, yeah, the period just increases by 2. But no, it's opposite. What happens? It decreases by a factor of a half. So the period is going to be pi divided by 2. You need to understand that that affects the location of your vertical asymptotes. That affects the location of your vertical asymptotes. They're no longer going to be at negative pi halves and pi halves and 3 pi halves. Because if they're there, then you have a period of pi. We need a period that's half of that. Keep going with that. So what if we put one at pi 4s? Where would the other one be on the other side? Negative pi 4s. How do we know that's where they need to be? The graph hasn't moved to the left or to the right, has it? So it's still going to pass through 0, 0, because the graph hasn't moved left or right or up or down. But we have to have vertical asymptotes. That's one way to do it. That's what a lot of students do. Let's just check this, though. Is the horizontal distance between there and there pi halves? Yeah. So that's the correct period. I'm a little less strict on how much you have to label on a tangent function. You have to label the vertical asymptotes on either side of 0, 0. You also have to label these in-between points right there. What's in between 0 and pi 4ths? Pi 8ths or negative pi 8ths. Where is the graph at pi 8ths? It's at 1. At pi 8ths, it's at 1. At negative pi 8ths, it's at negative 1. There's one cycle right there. Let's do another example with cotangent. We've just been doing tangent. Let's do cotangent. Y equals the cotangent of x. Very similar. There are an infinite number of vertical asymptotes. They're in different spots. Why do they have to be in different spots? Why can't they be in the same spots then? Well, it's because cotangent's defined differently. Tangent is y over x. What's cotangent? X over y. So this one is going to have vertical asymptotes wherever y equals 0. So look at your unit circle. Where does y equal 0? Vertical asymptotes. Two pi and pi, I would agree with you, but we're missing one important one. 0. We have one at 0, we have one at pi, we have another one at 2 pi. Where else would we have vertical asymptotes? Negative pi, negative 2 pi. What about negative 0? Just seeing if you're listening.
Wouldn't it be like,
I feel like you do that and then realize that it doesn't be making notes, so then you just blame that on. It's like, oh, I just make sure I listen.
You feel like that's what I'm doing?
Yes. Maybe it's because you're already talking.
Yeah.
Probably.
So let's start putting some of these vertical asymptotes on there. Oh, the cotangent has the same period as tangent. It only takes a distance of pi to start repeating itself. For the same reason, if you're in the first quadrant, y and x are positive. If you're in the third quadrant, y and x are negative. Dividing either of those would give you the same value. So the period is pi. Now, would it be possible for cotangent then to start at 0, 0 like tangent? It can't start at 0, 0. Why? That's what one of our vertical asymptotes are. So the cotangent isn't actually starting at 0, 0. So let's make one of our cycles be between these two vertical asymptotes, between 0 and pi. Halfway between that is pi halves. Where is cotangent of pi halves? Look at your unicircle. Pi halves is 90 degrees. Remember, the definition of cotangent is x over y. So it's 0. So the cotangent passes through the x-axis at pi halves. And just for sake of time, I got to speed this up. If you cut this up into equal intervals on either side, what's the low? How do we mark those? Pi 5, or I can't even write here. Pi 4s and 3 pi 4s. It actually has the opposite shape. It comes up like this and goes down in this direction. Yeah, so if that's 1, and if that's -1. And it looks like that. That's one cycle. If we went in between here, then we have 3 pi halves. And again, it would look the same there. Over here we have negative pi halves. The graph would look like that. Those are some cycles of the cotangent. So let's take a look at this one. Y equals 3 times the cotangent of x over 2. Y equals 3 times the cotangent of x over 2. The period would be pi, not 2 pi, but pi over 1/2, which is 2 pi. What about an amplitude? There is no amplitude. However, we are still going to make use of this 3 here in a second. I'll show you what I mean by that. Where are the vertical asymptotes? There's still one at 0. But now, rather than going a distance of pi and putting an asymptote there, that's not where the cycle ends. Where does the cycle now end? 2 pi. So we go over to 2 pi. And we go over to 4 pi. There's another cycle that ends at 4 pi. I really only need you to do one cycle, but if you want to do 2, you can. Okay, so halfway between our cycle, between 0 and 2 pi, halfway there would be pi. If you break that up, you're going to have pi halves and 3 pi halves. And now, even though cotangent nor tangent, they don't have amplitudes, you still now make use of the 3. What does the 3 do to the graph? It still affects it. It's a vertical stretch, right? Usually halfway between, we just went up a distance of 1 and down 1, right? Now we just go up 3 and down 3 at those halfway points. So at pi halves, we're at a distance of 3. At 3 pi halves, you're at a distance of -3. So that's how you use that. It's not an amplitude, but it still does affect the graph vertically. It stretches it up. Okay. Let's do cosecant. They're actually similar to both of these two types of functions, sine, cosine, and tangent and cotangent. They're similar to tangent and cotangent because they have asymptotes. What was the definition of secant? Sorry, cosecant.
1 over x. Or 1 over y.
It was 1 over. It was 1. It's a reciprocal of sine. Sine is y, so cosecant is 1 over y. So where is this going to have? Where is this going to have vertical asymptotes?
Too high, too high.
Wherever y is equal to 0. Now you can think about it that way. It's actually easier to think about it this way. If you're graphing a cosecant, graph sine first. Here's an example. Let's just graph y equals 2 times the cosecant of, I don't know, let's do x over 4. 2 times the cosecant of x over 4. The similarities here are that the period of the cosecant is the same as the period of the sine. So it has the same formula. Period is 2 pi divided by b. What's b in this case? 1/4. So the period is 8 pi. Now, as best you can, when you're graphing the sine function, maybe use a dotted line or just really lightly. So we're first going to graph the sine function. First graph 2 times the sine of x over 4. So we're going to end all the way out at 8 pi. Halfway is 4 pi. Halfway between that is 2 pi. Over here is 6 pi. And the amplitude is 2. I know I'm moving light speed here. I'm sorry. Now, if this were a sine function, where would it start? 0, 0. Where would the cycle end? 8 pi, comma, 0. And then it would be up at its highest point, down through 0, down at its lowest point. Now I'm going to graph this though with the dotted line because this really isn't what we're supposed to end up with, but this will help us get the shape of the cosecant. So there's the sine function in a dotted line. Wherever this sine function crosses through the x-axis, that's where you place your vertical asymptote. So there's going to be 3 of them. 1 right here, 1 right here, and 1 right there. Anytime that graph would have crossed through the x-axis, that's where you place your vertical asymptote. And like I showed you before, what did I show you before? Yeah. With the sine function here, this is where it's at its highest point. You flip it up. This is that reciprocal relationship between sine and cosecant. Reciprocal. Flip the fraction upside down, and then down here, so students sometimes get a little confused using this method. They think the graph is the black and the blue part. Is the blue part of the answer? No, it's simply there to help you get a nice shape for your cosecant. The graph that really matters is these 2 parts in black. This is the cycle, this part here and this part here. That's one cycle, both of them together. Okay? Because over here on the left you would have up and down, over here you have up and down, so both of those together count as one cycle. Okay? Secant would have been the same as graphing a cosine. Yeah. Well, it never goes through these asymptotes. Is that what you're talking about? Yeah. Because with 1 over y, y is never going to be 0. That would make it undefined. Yeah. We, bell's going to be ringing here. Just real quick to wrap this up. If I had replaced this with secant, you need to pay attention to this. If I had replaced this with secant, what would the process have been? Graph cosine, and then just flip them up. Flip the highs up, the lows down. It's the same process. with cosine, let's say this was your cosine graph, right? So you'd have a vertical asymptote here. You'd have a vertical asymptote there. So then this, half of it would flip up there. The full piece would flip down there. And then here, half of it would flip up there. There is. If this graph continued down that way, then it would flip up that way. That's where the graph.
Isn't it 1 over x?
That's where the graph crosses through the x-axis. So that's where.
Isn't it x can't be 0? So like y can't be 0, like the same.